In this video, I will share how to use Grasshopper to create a pedestrian catchment for kids, which has a walking speed of 1 meter per second. So, first thing I'll do is I'll turn off everything. We'll use those things in another video, and I will also turn up, bring in the road network, or in this case is the pedestrian network of Fitzroy. You can get this data from OpenStreetMap, and we'll open up Grasshopper. Here I already internalized the data for the Fitzroy network, so what I'll actually do is I'll turn that off. And the component that we'll use for the pedestrian to create the pedestrian catchment is shortest walk. So what shortest walk do is that it needs a few things. I'll make that smaller. It needs the curve. The curve is the network that the path or the sidewalks. It needs a wanted path. The wanted path will be the ideal path that you want to walk, which is you need a starting point and an end point, and the line between those 2 points is the wanted path, which is the ideal path you will want to walk. But what shortest walk does is that it will try to follow the path that you want, but using the network you provided to find the shortest walk from the start point to the end point. Okay. So first thing we'll have to do is to identify a start point. And because we're analyzing for kids, my start point will be right here. You can't see the buildings, but here is Fitzroy Primary School. And we'll create the wanted path. So we also need a endpoint. So what's the endpoint here? The endpoint, because we're running the simulation for the whole network, so we actually need the endpoint for every single segment, every single point we can get. So we use the explode a component to get the point of every single segment. And using a line tool, we'll connect the start point to every single the vertices of every single segment. Here we go. That's what it will look like. So that's all the wanted path to every single point. I'll turn those off. I'll turn the network off as well. And after connecting all that to shortest walk, that's what we can get. All the shortest walk to every single point of the network. But there's an issue here. In a usual, in a normal pedestrian catchment, you'll want to run through every single path, every single network, and try to figure out in a certain distance how far you can go. But because we're using shortest walk, sometimes I'll turn back on the network, turn to a different color. Here, the green lines is the shortest walk. As you can see here, it is not going through some of the path. That's because the path it identified as that's not the shortest walk. So it will just not walk through it, and that's not ideal. The workaround is for that is we'll figure out in the 10-minute catchment for kids the outline of how far I can go. Maybe it will be like this. This is the distance that the kids can walk, and we create an outline of it, and we just assume that the path inside will be walked, which you'll see later once we get all the other things going. So with the shortest walk curves, right now what we're going to do next is to make the curves inside 600 meters, because we want to analyze for kids 1 meter per second walking speed and walk for 10 minutes. That will be 600 meters. So we want to make all the curves under 600 meters. So from the curve, we'll extract the length. I'll make a panel to visualize it. Here's all the length of the curves. You can see there's a lot of different length every single curve. And we run a larger than 600 to get all the curves that is larger than 600. And we use call pattern to get all that curve. So you connect the curve to the list, and you connect larger than or equal to the pattern. So there we have all the curves that is larger than 600 meters here. And we connect another length to it. Let's see if everything goes well. So here you can see every single curve is larger than 600 meters, 1000, here's 800. So we will try to narrow it down even more to closer to 600. So we'll run the call pattern again, but this time we'll use smaller than. So here we run a smaller than, I chose 800. So you connect the call pattern again to the list will be the first list of curves that is larger than 600. You connect to the second call pattern, and you connect the smaller than 800 to the pattern. And this is what we're left with. This is all the curve. I'll use the panel to show you the length again. Here you have all the curves that is larger than 600 but smaller than 800, which is good. But this is still not 600. This is still not a 10-minute catchment. So we'll have to shorten every single curve so that it matches 600 meters. So what we could do is we take the length of all these curves, we take the length, and we subtract it by 600 to get a result of the difference between the length of the curve and also 600. And we use a component called extended curves. So you connect all the curves to the curve, and type, I think you can just leave it, which is line. And so the start point will be the midpoint. That is from the shortest walk. So the start point will be something here, somewhere there. And what we're trying to do with the extend curve is from the endpoint, we want to shorten it all the way to 600. So for the end, we'll have the results of the difference. We get a negative results of the distance, and we connect into the endpoint. So right now you could see it shortens everything to 600. Give it a length again to see the results. Length and panel. There we go. Right now you can see everything is 600. Every single line is 600, which is what we want.